Okay, so for this, we're going to look at a few problems from Chapter 18 and some of the thermodynamic stuff. So we're going to start with a standard molar entropy problem. So we want to calculate the standard molar entropy, delta S, of reaction for the following reaction. We have N2O4 plus 4H2 reacts to form nitrogen gas and 4 water molecules. The first thing to note is that we want to use the appendix in the back of our textbook to look up values for this. On your test, you'll have to look at them from a table in the back of your test. You're not expected to memorize delta S's for these things. So what we need to do is we know that our entropy value, let's get that to work, there we go, is going to be equal to, we're going to add up all the delta S values, or all the entropy values, not delta yet, for our products. And then we're going to subtract from that all the S values for our reactants. But remember, for each of these, we're going to worry about how many moles there are. So I'll have an N. And we're going to sum up each of the products and each of the reactants, not just one of them at a time. So that's why we're doing a summation. I should have left a little more room to plug that in better. So, okay, that means that for this problem, the delta S, so our standard molar entropy, is going to be, we have one nitrogen, so that's going to be 191.6 joules per mole Kelvin. And then from that, we're going to add the value for our waters, which we have 4 of, and each water has a value of 188.8 joules per mole Kelvin. Make sure to check that you're working with the right phase. So this is a gas, not a liquid, so grab the value for gas. Then we're going to subtract, I'm going to do this in the second line. And we're subtracting the whole thing, so I'm putting this in brackets, so we'll add everything together, and then we'll subtract at the end. So then we've got to look up N2O4. We find a value of 304.4 joules per mole Kelvin. And from that, we also have 4 hydrogen molecules, and those each give a value of 130.7 joules per mole Kelvin. Then all we have to do is add all this up in here, and then add all these up, and then subtract one from the other. And we're going to get that for our final answer, for our standard molar entropy, is going to be equal to 119.6 joules per mole Kelvin. So remember, whenever you look up an entropy value for just a single molecule or atom sometime, it's always going to be positive. But that doesn't mean that your delta S value has to be positive. Since we're going with products minus reactants, it is possible for entropy changes to both have more entropy and less entropy. Note that in this particular example, it would be hard to predict by just looking at it what the sign should be, because you have the same number of molecules on each side, and there's no obvious change in complexity. Some molecules are getting more complex, some less, and there's no molar mass change. So you can't tell just by looking at this one. You would actually have to look up values. Remember that for some of the other problems, especially multiple choice oriented, you'll have somewhere you're not expected to look up. You're just supposed to look at and go, okay, what do I think should happen to this, without having to do an actual calculation like this. But I'll make sure it's clear whether you're supposed to predict by looking at it, or whether you're actually supposed to calculate it with something like this, where I actually ask you to give a number rather than just look at a few and tell me. So let's look at this next. So we did that with delta S. Now we're going to do a lot of work with delta G. We end up talking about free energy, which is what delta G stands for, more in this chapter than entropy, although entropy is still significant. Make sure you're looking at those parts. So for here, we're asked, at what temperatures will this reaction be spontaneous? We have calcium solid plus oxygen gas forms 2 calcium oxide. So we're given the delta H and the delta S for this. So the first thing to look at is that our delta H is negative and our delta S is negative. What that means is that the reaction will not be spontaneous at all temperatures. Remember that if you have both negative or both positive, it means that sometimes it'll be spontaneous and some it is not, and there'll be a temperature where that changes at. When they are both negative, well, let's look at the equation to figure out this part out. So delta G equals delta H minus T delta S. And so something to keep in mind is that at lower temperatures, your delta H value is going to be larger than your T delta S. And then as temperature goes up, the right side of the equation is going to get bigger and bigger. Or at least you'll have a higher absolute value. It could be smaller and smaller if it's negative. So when you're at low temperatures, delta H is going to be the dominant factor, and it's going to have a negative sign. So that means at low temperatures, our delta G is going to be negative, because the negative for delta H is bigger than the positive for T delta S. And when we get to high temperatures, since delta S is negative, minus T delta S is going to create a positive term. So eventually there'll be some temperature where the right side of this equation becomes so big that the negative delta H isn't big enough to give us a free energy that is negative. So it will become non-spontaneous. So whatever temperature we solve for, that's going to be the highest temperature where this thing can be spontaneous. It'll be spontaneous there and everything below it. So to do that, we want to solve for when delta G is 0, because 0 is our changing point when we change from spontaneous to non-spontaneous. So I'm going to plug a 0 in for delta G. Then for delta H, we know that we're just given the value 1,269.8, 69, not 96. And that's in kilojoules. And then we're going to subtract from this. I'm going to have a temperature. We don't know, so we're solving for T. And then I'm going to multiply it by, and I'm going to convert this to kilojoules so the units are the same, negative 0.3646. And this is kilojoules per Kelvin now. We converted away from joules per Kelvin. So then I'm going to move the 1269.8 to the other side. So I have 1,269.8 kilojoules is equal to, let's see where, and then I had a minus, and then I had a negative here, so the two negatives become a positive, and I have 0.3646 kilojoules per Kelvin times temperature. We're then going to divide both sides by this 0.3646, and we're going to get that we have a temperature of 3,483 Kelvin is equal to our T. Note that this is not a final answer. You're not quite done yet. We actually have to use some words here. So this reaction will be spontaneous at temperatures below 3,483, and that's part of the answer because we have to make sure we looked at the signs. And so I got that by looking at the signs of delta H and delta S. If they had both been positive, I would have said it was spontaneous at temperatures above 3,483, which you could also just write this as T is less than 3,483. I would be okay. I would accept that answer as well. And so note that, yes, this number is huge, so it is spontaneous at a lot of temperatures, and that's okay. You will have some reactions where you have very large or very small temperatures, and that's okay. The other thing to keep in mind is that you might have signs where it's always spontaneous or never spontaneous. That's still possible with numbers like this. So you wouldn't actually have to solve for delta G is equal to 0. You would just look at the signs and go, oh, it's always spontaneous. For example, if delta H had been negative and delta S had been positive, the delta G would be negative for all values, so you wouldn't have to do the math. The answer would be it's spontaneous at all temperatures. So make sure to check that before you do this math and try to solve for 0. So having said that, let's solve another free energy problem. And so for this problem, we're given a situation where we have a reaction and we want to know what its delta G is, but you notice it doesn't have the little knot symbol. It is not a delta G. We don't have this knot. The reason for that is we're not working at standard conditions. We're given a set of pressures and they're not all 1 atmosphere. Now, having said that, to solve this problem, we need to start by solving for this free energy at the standard conditions because that's part of our full delta G equation. So I'm going to go ahead and solve for this one first. So this is equal to just products minus reactants. So we'll have 2 times the value for COCl2, which when I looked up was negative 204.9 kilojoules. Remember on your test, you'll either be given the delta G values here, or you'll have to look it up on an appendix sheet that's on the back of your test that you're able to pull off. So we've got this for our products. Now we're going to subtract our reactants. So again, big brackets. We got to subtract everything. So look up CO2. It's got a value of that you have 394.4 kilojoules. And I look up CCl4, and it's got a value of negative 66.4 kilojoules. So we're going to subtract both these and get a negative number, and then we're going to multiply these, and we're going to combine everything together. And we're going to get that the delta G, so under standard conditions, our delta G value is equal to 51 kilojoules. Now this is its standard, which if it hadn't given us these pressures, just ask for standard, you'd be done. But on the other hand, I need to solve for delta G reaction now. And that's going to be equal to delta G at standard conditions plus RT ln Q. So now I just have to plug this stuff in. We have 51 kilojoules plus, and then R is 8.314 times 10 to the negative 3 kilojoules per Kelvin. Remember, you've got to convert it into kilojoules because R, right, which was just 8.314, would just be joules, and that wouldn't match our value for delta G here. So you have to convert this value into joules or R into kilojoules. I like doing this in kilojoules because that's what delta G tends to be in. We have our temperature, which is 298 Kelvin. And we multiply this time, so we're still multiplying, I'm just writing it down below. The ln of Q, which is going to be, let's write our full Q up here. So Q is equal to products over reactants, so the pressure of COCl2 squared, because there's 2 of them, divided by the pressure of CO2 times the pressure of CCl4. So I've got to look up, so those values were given to me. So on top I have 1.24 squared divided by 0.245 times 0.123. Now I'm going to plug all these values in to my calculator, and I get a delta G reaction equal to 55.2 kilojoules. So this would be the answer. They asked for delta G reaction. The other possibility is they could have said, is it spontaneous or not? And then we should know that this is a non-spontaneous reaction because free energy change is positive. Make sure to always check the question because a number of them are going to ask you for both the delta G and then for you to interpret it. Is this spontaneous or not? And it could even be where they ask you, is it going to become spontaneous later? So that needs to be something that you're paying attention to when solving these problems. So let's do one more. This is where I want to calculate the delta G for a reaction. And we're given one reaction, this reaction here, and then we're given two component reactions we want to combine together. So remember, you can make changes to these and then add them together to try to get your final reaction. So in this case, what I want to do is the top reaction is currently written where the numbers match up with what I'd expect, right? Like there's one CO2 molecule here, and there's one in my final reaction. There's one calcium carbonate solid, one in my final reaction. But what's important is these are on the opposite sides. So I need to reverse my first reaction. So instead of the one I have, I want to write that calcium carbonate solid goes to my calcium solid plus carbon dioxide gas plus half an oxygen. And when I flip it, that also flips the sign of my delta G reaction, remember? And it's going to be equal to positive 734.4 kilojoules now. Sorry. Now for the second reaction, we need to do two things. It's also on the wrong side. Our calcium oxide should be on the product side. It's currently on the reactants. But the numbers are also too large. So we want to half everything. So we're going to multiply everything by a half when we reverse it. So then we're going to get half of an O2 plus one calcium solid goes to one calcium oxide solid. And when I do that, I get a delta G reaction equal to negative 603.3 kilojoules. Because I reversed the reaction, I changed the side from positive to negative. And when I halved it, I had to half the delta G as well. And if I had doubled it, I would double the delta G. Tripled it, triple the delta G. Now we want to add everything together and make sure it cancels out and we get the reaction. So here we have half an oxygen on the product reactant side and half on the product side. So those go away. Here we have one calcium on the reactant, one on the product. Those go away. And the other three only appear in one place, so we can just add them together. So we have calcium carbonate, solid, goes to... I'm trying to make an arrow. This should be an arrow. It doesn't look all that great. But that's an arrow, believe it or not. CO2 gas plus calcium oxide solid. And what we do is we notice that this addition matches with our equation we're targeting. So that means we've got the right two equations. And when we add two equations together, we also add their delta G values together. So we had a delta G of reaction equal to 131.1 kilojoules. And that will give us our delta G value. So remember, we can make adjustments to these if we've got the equations and then add them together. This is similar to Hess's law when you did this with enthalpies back in 1211. And if you want to go back and review Hess's law from 1211, that may help if you have trouble with doing this one.